The study of electric motor efficiency requires the use of a dynamometer, or something that can measure the mechanical energy output. For those of you who don't know, the dynamometer is a calibrated braking mechanism invented by a French mathematician and engineer named Gaspard de Prony in 1821. Even today, small dynamometers are still quite often referred to as a de Prony brake. So let's go into the lab, build a dynamometer, and use it to test an electric motor. Then we can see exactly what it does and why. Here's how it's done. If we want to understand how to measure the efficiency of electric motors, we have to be able to measure the mechanical output. For that, we need a dynamometer. Now, they don't build small dynamometers for small motors, so we have to build our own. So what we're going to need is a wheel of known circumference, a leather strap, 2 spring scales, a tachometer, a voltmeter, an ammeter, and a calculator. Let's see what this looks like. The first thing you need is a wheel of known circumference. In this case, we have machined this one so it's exactly 1 foot in circumference. And you need to have it to have a hole and a set screw in there so you can attach it to your motor, and every time it turns around, then we will have a calibrated length or distance that it's traveled. So the first thing you need is a wheel. The next thing you need is something to create a resistance against that wheel, and in this case we have used a thin strip of soft leather. And we've put a hole in each end of this so we can attach our spring scales to it. So the next thing you need is a small piece of soft leather. The next thing you need are 2 spring scales. And these are calibrated, calibrated spring scales that you can buy at Edmund Scientific or a number of other different kind of scientific supply stores. And these are adjustable so that you can get these to be relatively accurate. So you need 2 spring scales. The next thing you need is a tachometer, something that's going to measure how fast your motor is turning when you take the measurements of the resistance to turning it. So you're going to need a tachometer. You will also need to measure the volts and amps going into the motor so that we can understand how much electricity we are using to drive the motor. So these will measure our inputs. So you need a voltmeter and an ammeter. And finally, you'll need a calculator, something that we can take all of these numbers that we have taken and run them through an algebraic equation to determine the efficiency of the motor. So again, this is what you'll need. A wheel of known circumference, a piece of leather, 2 spring scales, a tachometer, a voltmeter and an ammeter, and a calculator. And from these, we can build our own dynamometer. Okay, here we are with our setup. We have the power supply driving the motor with our wheel attached, and we're going to run the dyno test. Now, what we're going to have to do this is we're going to have to take 4 measurements simultaneously. We're going to have to read the volts and the current while we also read the RPM and the deflection on the spring scales. So here, let me show you, as we do this, what this is going to look like. Got the spring scales here. I'm going to wrap the spring scales around here. And what's happening is that you can see, maybe you can see, maybe you can't see, but that the one in the back deflects down, whereas the other one is relieved because it's turning in that direction. So the front scale is still sitting at 0, but the back scale is reading about 600 grams deflection. And as you can see, it slows down and the current draw rises. So you can get an idea of what's happening here. You can tell that the motor's slowing down because the sound changes. You can see that the current rises. So we're going to take all of these measurements simultaneously to get an idea of the efficiency of the motor. So here's another shot of the dyno test showing that there's almost no deflection on the front spring and about 700 grams on the back. You can see how much it's pulled the back spring down and how much it's relieving this one. It's still sitting basically at zero. Okay, so let's take some measurements and see what we get. We'll put the strap with the spring scales on, and you can see where I've got them. I'm holding them both with one hand. And I've got the tachometer here, and I'm going to shine my spot on here. And I'm going to bring the current up to 7 amps, right like that. And there's my readings, 1864, about 1868. I have a deflection on the scales of 700 grams, and there's my readings before my strap gets too hot like a burner. So you have to take all 4 measurements simultaneously, and now we can calculate. Okay, so here are the measurements we saw on the bench. Our input was 12.1 volts at 7 amps, and that comes to a total of 84.7 watts input. We know that 1 horsepower is 746 watts, so when we divide our measurement here, 84.7 watts by 746 watts per horsepower, we get that our electrical input was the equivalent of 0.1135 horsepower. Our outputs were measured as 1864 RPM and 700 grams of deflection on our spring scales. Now the first thing we have to do is convert these two quantities to what we need, and we're going to measure the horsepower mechanically in foot-pounds per second. So we have to first convert the RPM into feet per second. So we know that our wheel is 1 foot in circumference, so 1 revolution equals 1 foot. So RPM is revolutions per minute, so if we divide that by 60 seconds per minute, we get revolutions per second. And for our wheel, revolutions per second equals feet per second. So we can take our RPM, 1864, divide by 60, and get 31.06 feet per second. The second thing we must do is convert grams into pounds. 1 pound equals 454 grams, and we measured 700 grams, so when we divide that by 454 grams per pound, we get 1.54 pounds. So continuing, we take our 31.06 feet per second, multiply that times 1.54 pounds, and we get our total mechanical measured output at 47.88 foot-pounds per second. So we know that 1 horsepower equals 550 foot-pounds per second, so when we divide this, we get our total measured mechanical output at 0.087 horsepower. Efficiency equals output divided by input. So here are our outputs and inputs, and when we divide these quantities, we get this fraction 0.767. We multiply that times 100, so we get our measured efficiency of 76.7%. Not bad for a 1/10 horsepower motor test. Okay, you just saw me demonstrate the dynamometer test. You may have noticed it is pretty hard to take all 4 measurements simultaneously by hand. Obviously, I could have gotten a more accurate measurement if the spring scales were hanging from a fixed bracket with a preset tension. Then it would be simple to speed the motor up to the point where the front spring scale read 0 and all the tension was on the back spring scale. An RPM reading could be taken with a tachometer at this point, with all the values remaining stable for accurate recording. But right now, I'm just trying to demonstrate the fundamental effects, so precision measuring is not absolutely required. If you were watching closely, you might have thought that the current reading was slightly higher than 7 amps. But for our purposes, the numbers I'm using are adequate, and our calculations are pretty close. need is a wheel of known circumference, a leather strap, 2 spring scales, a tachometer, a voltmeter, an ammeter, and a calculator. Let's see what this looks like. The first thing you need is a wheel of known circumference. Small dynamometers are still quite often referred to as a de Prony brake. So let's go into the lab, build a dynamometer, and use it to test an electric motor. Then we can see exactly what it does and why. Here's how it's done. If we want to understand how to measure the efficiency of electric motors, we have to be able to measure the mechanical output. For that, we need a dynamometer. Now, they don't build small dynamometers for small motors, so we have to build our own. So what we're going to need The study of electric motor efficiency requires the use of a dynamometer, or something that can measure the mechanical energy output. For those of you who don't know, the dynamometer is a calibrated braking mechanism invented by a French mathematician and engineer named Gaspard de Prony in 1821. Even today,